Hello everyone and welcome to another IB Physics video. Today we'll be looking at a paper 2 exam from May 2021, Timezone 1. So let's get started. In question number 1, it says that two players are playing table tennis. Player A hits the ball at a height of 0.24 meters above the edge of the table, measured from the top of the table to the bottom of the ball. The initial speed of the ball is 12 meters per second horizontally. Assume that air resistance is negligible. Part A says, show that the time taken for the ball to reach the surface of the table is 0.2 seconds. So we'll be using Subat equations for this, where the vertical displacement is equal to initial velocity plus 1/2 acceleration times time squared. Now we only want to calculate the vertical motion. So the vertical initial velocity is going to be 0. The vertical acceleration is 9.81. That means that the time taken is going to equal to the vertical height, which is 0.24 meters times 2 divided by 9.81. And everything's under the square root sign. This means if you use a calculator, you should get about 0.22 seconds, which is approximately 0.2 seconds with a precision of one significant figure more. So two significant figures. Part B says, sketch on the axis a graph showing the variation with time of the vertical component of velocity of the ball until it reaches the table surface. Take g, the gravitational acceleration, to be positive 10 meters per second squared. So we will start at 0, 0 at the origin. It will be a straight line that ends here. Part C, the net is stretched across the middle of the table. The table has a length of 2.74 meters and the net has a height of 15.0 centimeters. Show that the ball will go over the net. So first thing, the length of the table being 2.74 meters means that the distance to the net is exactly 1/2 that. Next, we'll try to find the time it takes for the ball to reach the net. This would be the time t required is the distance divided by the velocity. The distance again is 1/2 the length of the table divided by the velocity of 12 meters per second. In this case, we're only looking at the horizontal motion. This would be approximately 0.114 seconds. Next, we'll calculate how far the ball falls within this time. So the drop distance is equal to 1/2 acceleration times time squared. Again, the initial velocity vertically is 0. Sorry, this is the vertical drop distance. This is 1/2 times the gravitational acceleration, 9.81, times the time of 0.114 seconds squared. This means the ball is able to drop 0.065 meters, which is 6.5 centimeters from the initial height. Using this, we'll find the final height. The final height is the initial height minus this change in the height. Initial height is given by the problem as being 0.24 meters. The change in the height is what we found here, 0.065 meters, making the final height 0.175 meters, which is 17.5 meters. The final height is greater than the height of the net, which we will call is 15 centimeters. Therefore, the ball goes over the net. Part D of question 1 says the ball bounces and then reaches a peak height of 0.18 meters above the table with a horizontal speed of 10.5 meters per second. The mass of the ball is 2.7 grams. Part 1, determine the kinetic energy of the ball immediately after the bounce. We will use the conservation of energy. So the energy after bounce will equal to the energy at the peak. This will be the initial kinetic energy plus the initial potential energy, and will equal to the final peak kinetic energy at the top plus the final potential energy at the top as well. This initial potential energy is 0 because when it hits the table, the height is 0. So the kinetic energy will equal to 1/2 the mass times velocity at the peak, which is going to be 10.5 meters squared, or 10.5 meters per second, plus the mass times the gravitational acceleration times the height of 18 centimeters. Substituting with the values, we have 1/2 times 2.7 grams is 2.7 times 10 to the negative 3 kilograms multiplied by 10.5 meters per second squared, plus the mass is again 2.7 times 10 to the negative 3 kilograms multiplied by the gravitational acceleration 9.81 and the height of 0.18 meters. Using the calculator, you will find that the energy or kinetic energy would be 0.15 joules. In the next question, part 2, player B intercepts the ball when it is at its peak height. Player B holds a paddle or racket stationary and vertically. The ball is in contact with the paddle for 0.010 seconds. Assume the collision is elastic. Calculate the average force exerted by the ball on the paddle. State your answer to an appropriate number of significant figures. So, first things first, if it's an elastic collision, it will be moving to the left at the same velocity. It's 10.5 meters per second. In order to find the average velocity, you can use the impulse over time, the impulse being the mass times the change in velocity. The mass was 2.7 times 10 to the negative 3 kilograms, which is 2.7 grams. Now here's the thing. The change in velocity is twice the initial velocity because this would be 10.5 minus negative 10.5, which is 2 times 10.5 meters per second. The time required for this is given also as 0.010 seconds. And finally, you would find that this average force would be 5.67. If you look at the values, here's 2 significant figures, 3 significant figures, 2 significant figures. You should probably round this to 2 significant figures then. Moving on to question number 2. A planet is in a circular orbit around a star. The speed of the planet is constant. The following data is given. The mass of the planet, the mass of the star, and the distance from the star to the planet. A. Explain why centripetal force is needed for the planet to be in a circular orbit. Now this is a 2-point question, but there's a lot of things you can write. Number 1, if the net force were to be 0, the path of the planet would be in a straight line. Number 2, even though the speed is constant, moving in a circular path implies that the direction is changing, which means that the velocity is changing. Third, the acceleration required is towards the center of the circle. And there's other things you can add to this. You can say that the velocity and acceleration are perpendicular, or that the velocity and the force are perpendicular. B, it asks you to calculate the value of the centripetal force. First, the net force is equal to just the gravitational force, G m over r squared. And because there's no other forces, this will equal to the centripetal force. In this case, gravitational constant is 6.67 times 10 to the negative 11. The mass of the star was given to be 8 times 10 to the 24. Sorry, this is the mass of the planet. The actual mass of the star is 3.2 times 10 to the 30th divided by the distance, which is 4.4 times 10 to the 10, and of course squared. If you use your calculators, you can find this to be 8.8 times 10 to the power 23 newtons. In part C, a spacecraft is to be launched from the surface of the planet to escape from the star system. The radius of the planet is 9.1 times 10 to the 3rd kilometers. Show that the gravitational potential due to the planet and the star at the surface of the planet is about -5 times 10 to the 9th joules per kilogram. So, first, the net gravitational potential is the sum of the individual potentials. The potential of the planet plus the potential due to the star. In this case, gravitational constant times the mass of the planet divided by the radius of the planet. And it's going to be negative, plus, again, negative for gravitational potential, gravitational constant, mass of the star, just S, I guess, divided by the distance from the sun, from the star to the planet. If you factor out the gravitational constant, let's use negative 6.67 times 10 to the negative 11. You have the mass of the planet, 8 times 10 to the 24, divided by the radius of the planet, 9.1 times 10 to the 6th meters. Because this is kilometers, you multiply by 1,000, plus 3.2 times 10 to the 30th divided by 4.4. Distance to the planet would be times 10 to the power of 10 meters. You can calculate this to be negative 4.9 times 10 to the 9th. And the units are, of course, joules per kilogram. And as required, we found this value to one significant figure more precision. Part 2, estimate the escape speed of the spacecraft from the planet star system. So if you want to get the escape speed, the minimum kinetic energy required to escape must equal to the gravitational potential energy. And this has to be a positive value, of course, because kinetic energy is a positive value. So you can either put a negative here to cancel out the negative of the gravitational potential energy, or you can put an absolute value here. Either way, this becomes 1/2 the mass of the spacecraft times the escape velocity squared, and it will equal to the mass times the gravitational potential. Gravitational potential being something we have already calculated. Finally, escape velocity is equal to the square root of 2 times the gravitational potential, which is the square root of 2 times 4.9 times 10 to the 9th, which is what we found in the previous problem. And this is equal to 9.91 times 10 to the 4th meters per second. In this next question, question number 3, you have a mass of 1 kilogram of water and it is brought to its boiling point of 100 degrees Celsius using an electric heater of 1.6 kilowatts. Part A, Roman numeral 1 says the molar mass of water is 18 grams per mole. Estimate the average speed of the water molecules in the vapor produced. Assume the vapor behaves as an ideal gas. So first things first, we'll use the equation for the average kinetic energy as being equal to 3/2 times the Boltzmann constant times the absolute temperature. Next, this will be equal to 1/2 times the mass of one molecule times the average velocity squared. Finally, you would get this average velocity of the molecules would be the square root of 3 times the Boltzmann constant times the temperature divided by the mass. In this case, we'll use physics booklets has the Boltzmann constant of 1.38 times 10 to the negative 23. Absolute temperature would be at 100 degrees Celsius, 373 Kelvin. Next, we need the mass of one molecule. And there's 2 ways to get this. Grams per mole is the same thing or similar to an atomic mass unit. So it'd be 18 atomic mass units. And we know that one atomic mass unit is 1.661 times 10 to the negative 27 kilograms. So we can use that value here. 18 atomic mass units multiplied by 1.661 times 10 to the negative 27. Another way to find the mass of one molecule would be to use the fact that it's 18 grams per mole. 18 grams is 0.018 kilograms. And 1 mole is defined as Avogadro's number, 6.02 times 10 to the 23. Incidentally, this will give you the same result as this. So, if you use this to calculate, you get approximately a velocity of 720 meters per second. Part 2 says, state one assumption of the kinetic model of an ideal gas. And there's lots of. We can start with the atoms being point particles with negligible volume. We can also talk about the fact that ideally they should have zero intermolecular forces. They will also accept the corollary of this, which means that the potential energy of ideal gases will also be zero. Another assumption would be that the collisions are elastic. There's others as well. The fact that the velocities are random in both in magnitude and direction. They should obey the laws of mechanics, and that the time of collisions should be negligible compared to the time between collisions. Just remember one thing, in this question there's only 1 point, so you should only have one assumption, which also the question says just write one. But in part B, it says a mass of 0.86 kilograms of water remains after it has boiled for 200 seconds. Estimate the specific latent heat of vaporization of water and state an appropriate unit for your answer. So for vaporization, you have the heat required to vaporize a substance is equal to the mass of the substance times the latent heat of fusion of the substance, or latent heat of vaporization in this case. This would be the heat required per mass. And since you have the power, the heat is the power times the time required. And the mass would be the change in the mass. In this case, it powers 1600 watts, time is 200 seconds, and the mass is 1 kilogram minus 0.86 kilograms, because it's what remains, not what has boiled off. This gives us 2.3 times 10 to the 6th, and if you look at the units, it's joules per kilogram. Part 2, explain why the temperature of the water remains constant at 100 degrees Celsius during this time. So you are providing with thermal energy. Thermal. But this thermal energy is used to, well, number one, you can say break the bonds, break the intermolecular bonds between the atoms, or increase the potential energy. Either one is fine. This means that the kinetic energy is constant. And since the temperature is related to the kinetic energy, the temperature is also constant. Part C of this question says the heater is removed and a mass of 0.30 kilograms of pasta at negative 10 degrees Celsius is added to the boiling water. Determine the equilibrium temperature of the pasta and water after the pasta is added. Other heat transfers are negligible, and we're given the specific capacity of the pasta and the specific capacity of the water. So, let's write an equation. The heat transferred to the water plus the heat transferred to the pasta should add up to 0. That would be the mass of the water times the specific capacity of the water times the change of temperature of the water plus the mass of the pasta times the heat capacity of the pasta times the change in temperature of the pasta. If you put in the values, the water remaining we said was 0.86 kilograms times the heat capacity of the water. This is in kilojoules, so it's 4,200 joules per kilogram Kelvin. Now the change in temperature, if you use this format, it's always the final temperature minus initial temperature. Notice that because the final temperature is lower, this whole term would be a negative number, which is required because we need a negative plus a positive to equal to 0. You add this to the mass of the pasta, which is 0.3 kilograms, times the heat capacity of the pasta, 1,800 joules per kilogram Kelvin, times the change in temperature of the pasta, which would be the final minus initial negative 10. And all this is equal to 0. This becomes a very simple algebraic equation. There's only one unknown. The final temperature should equal approximately 85.7 degrees Celsius, or to do specific figures, 86 degrees Celsius. In part D, the electric heater has two identical resistors connected in parallel. The circuit transfers 1.6 kilowatts when the switch A only is closed. So, in this case, that means that all this power is transferred to just one resistor. Show that each resistor has a resistance of 330 ohms. We will use the equation where the power is equal to the voltage squared divided by the resistance. In this case, the power is 1600 watts, and it should equal to 220 volts squared divided by the resistance. And indeed, you get a resistance equal to 30.25 ohms. In part 2, it asks us to calculate the power transferred by the heater when both switches are closed. And there's two ways to do this. Of course, one is easier than the other. The first way you can do this is we can find the total resistance. It's 1 over 30 plus 1 over 30. Of course, this means the total resistance is simply 15 ohms. Again, we'll use the equation where the power is equal to the voltage squared over the resistance. 220 squared over 15 is in fact 3,200 watts. Now the second way you can do this is each resistor has exactly the same power. So power of resistor A is equal to the power of resistor B. And this is because they have exactly the same voltage drop. And they have exactly the same resistance. Which means one of them had a power of 1600. So if you have two of them, you should have the total power is simply 2 times the power of a single one. Just 2 times 1600 watts, which is 3,200 watts. Question number 4. A planet orbits at a distance d from a star. The power emitted from the star is P. The total surface area of the planet is A. Part A, Roman numeral 1, says explain why the power incident on the planet is given by this equation here. First, the intensity of the sunlight, of the light, is given by the power divided by 4 pi distance squared, which is of course the area of the sphere that uses the distance as its radius. Next, the intensity absorbed, the intensity absorbed actually, let's calculate the power absorbed by the planet. We're equal to the intensity of the light times the cross-sectional area of the object. Basically, the area of the shadow created by the object. In this case, we'll use this here. So power over 4 pi d squared. Now what about the cross-sectional area? The cross-sectional area is simply pi r squared, where r is the radius of the planet. But the area of the surface area of the whole planet is 4 pi r squared. This cross-sectional area is exactly 1/4 the surface area of the planet. So this cross-section area is equal to A over 4, which means put it here, and you get the equation that we are required to prove. Part 2. The albedo of the planet is alpha. The equilibrium surface temperature of the planet is T. Derive the expression for this equilibrium temperature. So, at equilibrium temperature, the power of thermal radiation should equal to the power absorbed from the sun or the star. The equation for thermal radiation is Stephen-Boltzmann's law, where E is equal to the emissivity, E times the Stephen-Boltzmann constant, times the area of the object, times temperature to the 4th power. And this should equal to the amount of light absorbed would be 1 minus the albedo times, again, the power P of the sun or the star over 4 pi distance squared times A over 4. Simplifying this for the temperature T, the areas incidentally will cancel out on both sides. You get the 4th root of 1 minus albedo, which is the fraction of light absorbed, times the power over 16, which is 4 times 4, pi times the distance squared, times emissivity, times the Stephen-Boltzmann constant. In part B of this question, it says, on average, the moon is the same distance from the sun as the Earth. The moon can be assumed to have an emissivity of E equals 1 and an albedo of alpha equals 0.13. The solar constant is 1.36 times 10 to the 3rd watts per square meter. Calculate the surface temperature of the moon. Now, we have previously found an equation for the temperature. The problem here is they are giving us the solar constant instead. So what we can do is we know the solar constant sort of constant S is equal to the power over 4 pi r, or 4 pi d squared. So if we apply this to this equation here, the temperature is almost exactly the same. It's 1 minus the albedo times the Solar constant. It's just that instead of having this term here, you have 4 emissivity times the 7 Boltzmann constant. This becomes 1 minus 0.13 times the Solar constant, 1360, divided by 4 times emissivity is 1, and the 7 Boltzmann constant, 4.5, sorry, not 4.5, 5.67 times 10 to the negative 8. This will lead us to an answer of approximately 268.75. Of course, we have to round, approximately 270 Kelvin. In this next question, question number 5, a device sends an impulse of electrical energy to maintain a regular heartbeat in a person. The device is powered by an alternating current connected to a step-up transformer that charges a capacitor of capacitance 30 microfarads. So this is a capacitor. It's connected to the transformer, and this transformer, of course, charges the capacitor. A, explain the role of the diode in the circuit. So a diode only allows current to flow in one direction. If you connect it to a transformer or AC power supply, what it would do is it would change the voltage time graph so that it only has the positive side. We call this half-wave rectification. And of course, what this allows it to do is this allows it to charge the capacitor without it being discharged. Because it does not, if the positive charges go in, the diode prevents the charges from flowing back out. In part B, the voltage across the primary coil of the transformer is 220 volts. The number of turns on the secondary coil is 15 times greater than the number of turns in the primary coil. Part 1, show that the maximum energy stored by the capacitor is about 160 joules. So, you have a transformer, number of coils. So we have the EMF in the primary side over the EMF of the secondary side. Is the number of turns in the primary side. And the number of turns in the secondary side is 15 times the number of turns in the primary. This means the EMF in the secondary side is 15 times the EMF in the primary side, which is 15 times 220, which is 3,300 volts. Next. The energy stored in a capacitor is 1/2 times the capacitance times the voltage squared. Gets 1/2. Capacitance is 30 microfarads, but this 30 times 10 to the negative 6 times the voltage 3,300 squared. the energy stored will be approximately 163 joules. Part 2, calculate the maximum charge stored in the capacitor. Again, charge is very simply the capacitance times the voltage. 30 times 10 to the negative 6 times 3,300, which is approximately 9.9 times 10 to the negative 6 coulombs. And, sorry, not negative 6, negative 2 coulombs, which is approximately 0.1 coulombs to one significant figure. Identify using the label positive on the diagram the polarity of the capacitor. So we actually already labeled it here, but if it goes like that, the positive charges will flow in, but when the transformer changes the direction, these will not be able to flow out. So the positive charges would be at the bottom side and negative charges on the top side. Part C, the switch is moved to position B. This means it's going to discharge. Number 1, describe what happens to the energy stored in the capacitor when the switch is moved to position B. So, capacitor discharges. And what happens then is the energy stored in the capacitor is transferred to the resistor. Now recall the resistor is actually the heart, so you can also say it's transferred to the heart. Part 2, show that the charge remaining in the capacitor after a time equal to one time constant of the circuit will be 0.37 times the initial charge. Part 2 of this question says that show that the charge remaining in the capacitor after a time equal to one time constant tau of the circuit will be 0.37 Q0, which is the initial charge. So first things first, we'll use the charge remaining will be equal to the initial charge times e to the power of negative time over the time constant tau. So if a time is equal to one time constant, the remaining charge is simply initial charge times e to the power of negative 1. Which is initial charge times 1 over e. We can say 1 over e is equal to 0.368. Therefore, the final charge is the initial charge times 0.368 as required. In the following question, Roman numeral 3 of question 5C, it says the graph shows the variation with time of the charge in the capacitor as it is being discharged to the heart. So we have the relative charge as a fraction of 1. And we have the time in milliseconds in the x-axis. Determine the electrical resistance of the closed circuit with the switch in position B. So we are initially given that if time is one time constant, then this ratio would be equal to 0.13. Was it? 0.37. So we have to find where this is equal to 0.37. This is units are 2. So it'd be somewhere approximately around here at 1.6 milliseconds. So you can say time constant is 1.6 times 10 to the negative 3 seconds is equal to the resistance times the capacitance of 30 times 10 to the negative 6. This would give us a calculation about 53.3 ohms. Just remember there will be a fairly big amount of uncertainty because of how difficult it is to read a precise number from the graph. Another thing you can do is you can try to say use 1 millisecond as a time. Time is 1 millisecond. And the ratio of the charge, or potential charge, would be, this looks to be about 0.5. So charge is initial charge times e to the power of negative time over the time constant. We have 0.5 is equal to e to the power of negative t over the time constant. We take the natural log of both sides. Let's actually just reduce this part. Natural log of 0.5 is equal to negative 10 to the negative 3 divided by resistance and 30 times 10 to the negative 6 for the capacitance. If you use this value, the resistance would be approximately 48.1. So the important part is you have to write down all your steps because the answers may vary. In part D, it says that in practice, 2 electrodes connect the heart to the circuit. These electrodes introduce an additional capacitance. So if you connect 2 electrodes and the capacitance is greater, they must have been in parallel. If you connect them in series, the total capacitance will be lower. Explain the effect of the electrode capacitance on the discharge time. So you have increased capacitance. And you can explain in 2 ways. You can either say that the stored charge is larger, or that the time constant is bigger. Regardless of which of these you choose, the discharge time would be longer. Question number 6. A painting is protected behind a transparent glass sheet of refractive index N sub glass. A coating of thickness W is added to the glass sheet to reduce reflection. The refractive index of the coating is such that the refractive index of the glass is greater than the refractive index of the coating, which is greater than 1. The diagram illustrates rays normally incident in the coating. The incident angles in the diagram are drawn away from the normal for clarity. Part A, state the phase change when a ray is reflective at B. So at B, the index refraction of the glass is greater than the index refraction of the coating. So there is a phase shift. Of either 180 degrees or pi radians. Part B, explain the condition for W, which is the thickness, that eliminates reflection for a particular light light wavelength in air, lambda air. So number one, in order to minimize or eliminate reflection, you have to have destructive interference. Number two, in order to know which equation you should use, you have to determine that both reflections at A and the reflection at B force a phase shift of pi or 180 degrees. Which means you cannot use the equations in the physics booklets as is. You have to use the equation of 2dn green equal to m plus 1/2 lambda. In the physics booklets, it would say that this should be applied for constructive interference, but because it's not the same condition, it's if both reflections are phase shifted, this is destructive interference instead. Part C, Roman number 1, it asks you to state the Rayleigh criterion for resolution. So, the Rayleigh criterion states that the angle of separation between two objects or the central maxima of these lights should be greater it needs to be greater than the angle to the first minimum. In order for these two objects to be resolved. For part 2 of this question, the painting contains a pattern of red dots with a spacing of 3 millimeters. Assume the wavelength of red light is 700 nanometers, and the average diameter of the pupil of a human eye is 4 millimeters. Calculate the maximum possible distance at which these red dots are distinguished. First of all, the angular separation has to be greater than or equal to the angle to the first minimum. This is a Rayleigh criterion. Now, it's not a slit, a pupil is circular, so we add the factor of 1.22 here. We'll use the approximation for the angular separation, which is the distance between the dots divided by the total distance from the eye to the painting. In order to maximize this distance, it has to be equal to, and the angle to the first minimum is simply the wavelength divided by the diameter of the pupil. So here, reorganizing this, the maximum distance will be equal to the distance between the dots times the pupil diameter divided by 1.22 times the wavelength. Let's sub with the values. 3 millimeters is 3 times 10 to the negative 3 meters times 4 millimeters, which is 4 times 10 to the negative 3 meters divided by 1.22 times 700 nanometers is 7 times 10 to the negative 7 meters. Using your calculator, you'll find this to be approximately 14 meters. Next, question number 7. Radioactive uranium-238 produces a series of decays ending with a stable nuclide of lead. The nucleus in this series decay by either alpha or beta minus decay. Part A. Uranium-238 decays into a nuclide of thorium-234. Write down the complete equation for this radioactive decay. So first, the product is thorium, Th, 234. Now, it went from 238 to 234. So it must have been alpha decay. Entering alpha decay, the number of protons is reduced by 2, so it's 90. Like so. Part B, thallium decays into lead-206. Identify the quark changes for this decay. So let's start with looking at what happens here. Notice that if you start with thallium, 206, 81, becoming lead, 206, this is 82. In order to keep the charges the same on both sides, you have to add an electron, here, and an anti-electron neutrino. Okay. So basically, you're adding a proton, so a neutron is turning into a proton. So let's write the quark content of a neutron, which is up, down, down. Total charge is 0, and you use only the quarks in generation 1. This becomes an up, up, down, plus the electron, plus the neutrino. This implies that a down quark just turned into an up quark. Part C, the half-life of uranium is about 4.5 times 10 to the 9 years. The half-life of thallium is 4.2 minutes. Comparing contrasted methods to measure these half-lives. So what they want you to see here is that you will not be able to see any changes in the total fraction of number of uranium atoms or the activities, because you would have to wait for 4.5 billion years for them to halve. But in the case of thallium, it's a relatively easy thing to just wait 4.2 minutes and actually measure it, either the activity or the number of remaining thallium atoms, to see what the half-life is. So, how do you get the half-life of uranium without having to wait one full half-life then? Well, we know the activity is equal to the decay constant times the number of atoms. And we can use the decay constant to find the half-life. So for uranium, 238, one needs to measure both the activity and the number of atoms. What about for the thallium? For thallium, just the activity must be measured repeatedly over a period of time. And then you measure when the activity reaches half the original activity, and that would be the half-life. The same can be done not just with the activity, but with the remaining number of thallium atoms. Part D. The graph shows the variation of the nucleon number A of the binding energy per nucleon. So we have the binding energy per nucleon in megaelectron volts in the y-axis, and the number of nucleons, or the nucleon number, in the x-axis. Part 1. Outline why high temperatures are required for fusion to occur. So, for fusion to occur, the atoms need sufficient kinetic energy to get close enough to overcome the electrostatic repulsion of the nuclei. And finally, since the kinetic energy is proportional to the temperature, this would require a very high temperature. Part 2. Outline with reference to the graph why energy is released both in fusion and in fission. So, in order for energy to be released, what has to happen is the average binding energy of the products has to be higher than the average binding energy of the reactants. Simply, as long as the binding energy increases, energy will be released. In the following question, in part 3, uranium-235 is used as a nuclear fuel. The fission of uranium-235 can produce krypton-89 and barium-144. Determine in megaelectron volts and using the graph the energy released by this fission. So first, we'll look at the graph, and I copied it below so we can use it more easily. And we will find the binding energies per nucleon of each of these 3 elements. So first, let's look for the binding energy per nucleon of uranium-235, which will be around here in the graph. So I'll draw a vertical line upwards, and where it intersects at around 7.6 megaelectron volts would be the binding energy per nucleon of uranium-235. Now, barium is at 144, which is around here. So let's draw a vertical line. And it intersects around here. So let's estimate this to be 8.3 megaelectron volts. And this was for barium 144. Last we have krypton-89, which would be approximately around here. And this would be approximately 8.6 megaelectron volts. And this is for krypton 89. Okay. We'll use these binding energies per nucleon in order to find the energy released. First, the energy released is calculated by getting the total binding energies of the products minus the binding energies of the reactants. So what are the products? Products are krypton and barium. So we have 89 nucleons of krypton times 8.6 megaelectron volts per nucleon, plus whatever the binding energy for barium is 144 nucleons multiplied by 8.3 megaelectron volts per nucleon. Finally, we'll subtract the reactant binding energy, which is uranium-235 plus 235 nucleons times 7.6 megaelectron volts per nucleon. Using these values, you would get approximately 160 megaelectron volts. Now, you're not expected to get exactly this value. You have a lot of leeway because using the graph, you have a little bit of uncertainties. This is why you should probably write down all the values I have used. This one, and this one, so that they know what you used and you don't get a random value at the end. Okay. For the next question, it says that on the guitar, the strings played vibrate between 2 fixed points. The frequency of vibration is modified by changing the string length using a finger. The different strings have different wave speeds. When a string is plucked, the standing wave forms between the bridge and the finger. Outline how a standing wave is produced on the string. So you have to, first of all, you have to say that there's a traveling wave that is formed. Now, this traveling wave reflects from one of the bridges. And when it reflects, now you have 2 waves. The traveling wave and the reflected wave superimpose or interfere. Finally, not all these waves will stick around. If the wavelength meets boundary conditions, or put more simply, if the wave fits inside the string, then you can form standing waves. Part B, the string is displaced by 0.4 centimeters at point P to sound the guitar. Point P on the string vibrates with simple harmonic motion in its first harmonic with a frequency of 195 Hertz. The sounding length of the string is 62 centimeters. Show that the speed of the wave on the string is about 240 meters per second. So first, at the first harmonic, you have 1/2 of a wavelength fitting inside the length of the string. So this means that the wavelength is equal to 2 times 0.62 meters, which is 1.24 meters. In order to find the velocity of the wave, you have the frequency times the wavelength, which is 195 Hertz multiplied by 1.24 meters. And you get approximately 242 meters per second. Part 2, sketch a graph to show how the acceleration of point P varies with its displacement from the rest position. I'll highlight that this is simple harmonic motion, and for simple harmonic motion, the acceleration has to be proportional to the displacement in opposite direction, which means a straight line to the origin with a negative slope. Part 3, calculate in meters per second the maximum velocity of vibration of point P when it is vibrating with a frequency of 195 Hertz. So you have in the physics booklet that the velocity depends, of course, on the time and the angular velocity, which is angular velocity times the amplitude times the cosine of the angular velocity times time. So this will give you all the velocities at any point and any time, but you only want the maximum. Since this part, the cosine has a maximum of 1, the maximum value would simply be the angular velocity times the amplitude. In this case, we know that the angular velocity is 2 pi times the frequency. So let's replace that. 2 pi times the frequency times the amplitude. And we have all the information we need. 2 pi times 195 Hertz multiplied by 0.4 centimeters, which is 4 times 10 to the negative 3 meters. And the maximum velocity will be about 4.9 meters per second. Problem number 4, it says calculate in terms of g the maximum acceleration of this point. Same thing here. The acceleration maximum is equal to the angular velocity squared times the amplitude. Next, angular velocity is 2 pi times the frequency, and you square this, and multiply by 0.004 meters here. This will give us an angular acceleration about 6,005 meters per second squared. But it says in terms of g. G is just the gravitational acceleration, 9.81. So we have to use a unit conversion. We want this to have units g. 1g is 9.81 meters per second squared. We can see that the meters per second squared units will cancel out, and you'll be left with the units for g. So this divided by this is approximately 612 g. And you can just do one or two significant figures. You can estimate this to be about 600 g's. Part 5, estimate the displacement needed to double the energy of the string. Well, the total energy is equal to 1/2 the spring constant times the amplitude squared, or 1/2 mass times angular velocity squared times displacement squared. But this simply means that it's proportional to the displacement or the amplitude squared. That means if you want to double the total energy, you have to multiply the amplitude by the square root of 2. So amplitude times the square root of 2 would be 4 millimeters times square root of 2, and 5.66 centimeters, which is approximately, or millimeters, sorry. This is millimeters, which is approximately 6 millimeters to one significant figure. Part C. The string is made to vibrate in its third harmonic. State the distance between consecutive notes. Let's draw the string first. This string from here to here is 62 centimeters. At its third harmonic, we have, something like this. So it's divided into thirds. This is the distance between two consecutive notes, D. D is exactly 1/3 of the length of the string, which is 62 divided by 3. So approximately 20 centimeters. Question number 9. The conservation of energy and conservation of momentum are two examples of conservation laws. A. Outline the significance of conservation laws for physics. Now this is just a 1-point question, so any answer would suffice. You can say that they express fundamental principles of nature, they allow you to model situations, they allow you to calculate unknown variables, it allows you to predict some outcomes, it allows you to predict missing quantities or particles, or allows you to compare different systems or states. So there's too many, so I'm not going to just write down all of them. But if you move on to the next one, it says when a pi meson, which is pi negative, and a proton with a quark quantum given, and they collide, a possible outcome is a sigma baryon and a kaon meson. Apply 3 conservation laws to show that this interaction is possible. So the 3 that we're going to apply here is going to apply the conservation of charge. We apply the conservation of baryon number. And we will apply the conservation of strangeness. Now, the other ones, if you apply the conservation of lepton family number, that will also work, but it's kind of redundant because all the terms are 0. So let me just add it here. Okay, so let's write down the reaction first. We have a negative meson plus the proton, positive. They collide, and you get the sigma baryon plus the kaon meson. So let's look at the charge. The charge here is negative 1e. This is positive 1e, 0 and 0, and these are in fact equal to each other. What about the baryon number? The baryon number for pion is 0. The baryon number for proton is +1. The baryon number for the sigma baryon, of course, is also +1 because it's a baryon. And the kaon is a meson, so it's 0. So 1 equals 1. What about strangeness? There's 0 strangeness for the pion. There's 0 strangeness for the proton. The baryon, sigma baryon, has 1 strange particle, which means this is -1. And the kaon meson has a +1 strangeness. So again, 0 equals 0, so it checks out. I'll just highlight the checks. If you do lepton family number, they are all zeros. So 0 equals 0. Question number 10. In an electric circuit used to investigate the photoelectric effect, the voltage is varied until the reading in the ammeter is 0. The stopping voltage that produces this reading is 1.40 volts. Describe the photoelectric effect. So first, you might want to state that the photon has an amount of energy, right? Photon energy, photon equals HF. So what happens if this amount of energy is greater than the amount required for electron to escape? This photon will be absorbed. Actually, let's write this last word here. What happens if it doesn't have enough energy for electron to escape, it will not be absorbed, basically. If it's absorbed, then the electron will escape the atom. For the material and be emitted. So the electrons that are able to absorb these photons escape the substance and are emitted as photoelectrons. It says, show that the maximum velocity of the photoelectrons is 700 kilometers per second. So the maximum kinetic energy can be calculated using the stopping voltage multiplied by the charge of an electron. And because if you're able to calculate this, this is equal to the kinetic energy, 1/2 the mass times the velocity maximum squared. Getting the equation for the maximum velocity. Actually, let's change this to look different from the voltage. The maximum velocity will be the square root of 2 times the charge of an electron times the stopping voltage divided by the mass of the electron. So it's 2 times 1.6 times 10 to the negative 19 times the stopping voltage of 1.4 volts divided by 9.1 times 10 to the negative 31 kilograms for the mass of the electron. Everything under the square root. This would give you about 702,000 meters per second, which is 702 kilometers per second. In this next question, part C, the photoelectrons are emitted from a sodium surface. Sodium has a work function of 2.3 electron volts. Calculate the wavelength of the radiation incident on the sodium. State an appropriate unit for your answer. So, remember that the energy of the photon is divided into 2 purposes. First, it's used for the to pay for the amount of energy required to escape from the atom, and the remainder becomes kinetic energy. An equation for the energy of the photon would be the Planck's constant times the frequency, but we want to find the wavelength, so we're going to change the frequency to the speed of light over the wavelength. Next, this will be equal to, well, the kinetic energy is the charge of an electron times the stopping voltage. The wave function, the work function is simply 1.4 electron volts. Oh, sorry, not 1.4, 2.3 electron volts as given in the problem. So we have the wavelength as being Planck's constant times the speed of light divided by 2.3 plus 1.4 electron volts, which is simply 3.7 electron volts here. Now, you don't have to calculate the Planck constant times the speed of light and convert to electron volts. You have this value in the physics booklet. It would be 1.24 times 10 to the negative 6 electron volts meters. Using this value, you get that the wavelength should be 3.35 times 10 to the negative 7 meters, which is 340 nanometers. That's the last question, so that's it for today. Thank you for watching and see you next time.